Hello friends, in this video I'd like to solve the following problem from the International Mathematical Olympiad 1987, problem number 1, which was proposed by West Germany. Let S be a set of n elements and let Pn of k be the number of permutations of set S having exactly k fixed elements. We wish to prove that a. Sum going from k equals 0 to n of k times Pn of k equals n factorial, and likewise, sum going from k equals 0 to n of k minus 1 squared, Pn of k also equals n factorial. And small remark, only part A was given on the actual competition to the participants. Part B was shortlisted. Both parts were proposed by West Germany. It's a nice problem combining combinatorics with some manipulations and so on. Here are my hints. Sorry, wrong. Yes, here it is. We say that x is a fixed point of a mapping going from x to x if f of this element equals itself. And also, the number of permutations, sigma, from the set S onto itself, having no fixed points, these permutations are called derangements, is denoted by n subfactorial. I use, it's not completely standard notation. You may also see this horrible notation, which I despise. I use notation proposed by the authors of concrete mathematics. N inverted exclamation mark, as in Spanish language, for example, denotes the number of permutations having no fixed points, fixed elements. Try to express Pn of k using k subfactorial and binomial coefficients. And first, you should justify that sum going from k equals 0 to n of Pn of k actually equals n factorial. And also, these two crucial facts are very helpful. Namely, you should easily verify that k times n choose k equals n times n minus 1 choose k minus 1, and k times k minus 1 times n choose k equals n times n minus 1 times n minus 2 choose k minus 2. So give this problem a try, and I will see you in just a minute. Well, so I will proceed by several claims. My first claim number 1, is that Pn of k is actually n choose k n minus k subfactorial. How to prove it? Well, think combinatorically about it. We wish to count how many permutations have exactly k fixed points. So first, we need to choose these k points. So for example, we have n numbers, and we wish to fix k of them. So for example, we need to choose 2 out of 5, in general k out of n elements. How many ways are to do it? And choose k, obviously. And then we have no more fixed points, so the rest of elements, we have to have derangements of them. How many derangements are there of n minus k elements? By definition, n minus k subfactorial. So I'd say that it has been justified by now. My second claim number 2, is that sum going from k equals 0 to n, Pn of k, which also equals, as we know it, sum going from k equals 0 to n of n choose k n minus k subfactorial equals n factorial. How can we justify it? Well, think about it. On the left-hand side, we are counting every permutation, because every permutation has either 0 fixed points, or 1 fixed point, or 2 fixed points, and so on, up to n fixed points. So we are counting every permutation exactly once. Every permutation is counted exactly once. And then total number of permutations is n factorial. So this also must be true. Yes, it's a nice combinatorial reasoning. And now, after proving these two claims, I will maybe justify third claim, which will be useful. Claim number 3, k n choose k equals n minus 1 choose k minus 1. It's very easy to verify it. You just have to expand both sides. And also the second part of this claim is k minus 1 n choose k equals n minus 1 n minus 2 choose k minus 2. Both of these parts are very easy to verify. You just have to plug in, instead of n choose k, you plug in n factorial over k factorial n minus 1 factorial n minus k factorial, and you should easily verify that both of these claims are true. Alright, and now we can proceed to our solution. Part A. Let's start with part A, which was actually given on the Olympiad. We wish to compute this sum, going from 0 to n, k, pn of k. Well, as we know it, instead of pn of k, we can put n choose k, n minus k subfactorial. And now, using, so it's by claim number 1. By claim number 3, instead of k n choose k, we can put n minus 1 choose k minus 1 n minus k subfactorial. And now I will do a little trick. Also, one more thing, we can start summation at number 1, because for n equals 0, well, this is 0, so we can omit this term. So we can start summation at 1. Alright, so we have sum going from 1 to n. N is independent of the sum, so we can put it outside. And now I will do a slight trick. Instead of n minus k subfactorial, I will write n minus 1 minus k minus 1 subfactorial. And now I will shift my index of summation. So instead of k, I will put everywhere k plus 1. So this time k plus 1 goes from 1 to n, and here we have n minus 1, k plus 1 minus 1, n minus 1 minus k plus 1 minus 1 and subfactorial. And now it's sum going from 0 to n minus 1, n minus 1 choose k, n minus 1 minus k subfactorial. And now, using my claim number 2, we are exactly in this situation, but instead of n, we have n minus 1, which does not change the fact that this sum, by claim 2, it is n minus 1 factorial, which is n factorial. It's exactly what we wanted. Exactly what we wanted. Very nice. So that closes our proof of part A. Now let's move on to slightly harder part B. In part B, we wish to evaluate sum going from 0 to n of k minus 1 squared pn of k. Again, let's do the following. First, I wish to write my sum in the following way. It's k times k minus 1 pn of k minus sum going from 0 to n k pn of k plus sum going from 0 to n pn of k. I'm running out of space, unfortunately. Pn of k. All right. Is everything all right? Let's check. Well, here we have k squared minus 2k plus 1. Here we have k squared. Here we have minus k. Here we have another minus k, so it's minus 2k. And plus 1, we have plus 1. Everything is all right. And now, by claim number 2, this part right here is just n factorial. All right. Moreover, by our part A, which we have already demonstrated, this sum, part A, this sum is n factorial as well. So they actually cancel each other out, and we are left with sum going from 0 to n of k, k minus 1, and instead of Pn of k, we can put n choose k, n minus k subfactorial. Alright, and also let's notice that we can start our summation this time from 2, because if k equals 0, this vanishes, if k equals 1, this vanishes. Alright, and now using my claim number 3, instead of k minus 1 times n choose k, we can actually put n minus 1, n minus 2, choose k minus 2. And also I will change n minus k subfactorial to n minus 2 minus k minus 2 subfactorial. And now I will put n minus 1 outside of my sum, and again, just as in part A, I will shift my index of summation. So instead of k, I will put k plus 2 this time. So this time we'll get the following. Well, k plus 2 goes from 2 to n. Here we have n minus 2, k plus 2 minus 2. Here we have n minus 2 minus k plus 2 minus 2 subfactorial. Right. So this is n minus 1 times sum going from 0 to n minus 2, n minus 2 choose k, and here we have n minus 2 minus k subfactorial. Great. Because now using my claim number 2, if I'm not mistaken, claim number 2, this entire sum is just n minus 2 factorial. And n times n minus 1 times n minus 2 factorial, it's obviously n factorial, which closes our proof. It's exactly what we wanted. Both of our sums are equal n factorial. A pretty nice problem, not very complicated, but the crucial part was the observation that first we can change Pn of k, express it using subfactorials and the binomial coefficients, and also noticing that if we sum every Pn of k, we get n factorial. And actually, one more remark before you go. This equality right here, is actually a recursion for subfactorial. You can, because there is no nice formula for subfactorials. For n factorial there is, for subfactorial there is not. But you can actually find next subfactorial using this identity, knowing previous subfactorials. So it's a type of recursion, but not very effective because we have to sum all previous subfactorials. Anyway, thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.